Hey geometry students, today we're going to get into some of our logic rules, some of our logic properties that will be useful throughout the year. So number one, today we really get into deductive reasoning, this idea of we go step by step, and each step is has a justification. So this is a really solid type of reasoning, typically thought of as infallible. Although if you take a look, you can find deductive arguments for reasons for God's existence, and you can find deductive reasoning for reasons why God does not exist, and clearly both can't happen at the same time. So deductive reasoning does not solve all of our problems, but it is a good method to go through, and for the rest of geometry, at least this year, we will be using deductive reasoning to prove things. So we start that right now. One of the things that we're going to pick up in this unit, or in this lesson, is the law of detachment. So we'll just say if A then B, so a regular conditional statement. If A is true, then B is true. Okay, we'll say A then B. So if A is true, then B is true. Okay, we will assume that A is true, then we can conclude that B is true. The tough part here is that we are assuming A is true. Okay, sometimes A might not exactly be true, but if we have to assume that it is true, then that is true. The thing is, the place where our students make mistakes is if we say if A then B, A then B. Well, sometimes I'll say if A then B, B. Well, students will want to say that they can then conclude A, but that is not the case, and you'll see some examples of that. The transitive property goes like this: if A then B is true, and if B then C is true. So you have this connector here, this chain. This is also known as the chain rule. Okay, then we can conclude that if A is true, then C is true. Okay, so if you have ever seen those little storybooks, like if you give a mouse a cookie, if you give a pig a party, or if you give a moose a muffin, those are books that generally follow the transitive property, and that's actually going to be one of our little projects here at the end of chapter 2. All right, so some examples. Use the law of detachment, if possible, to make a valid conclusion in the true situation. So again, we are assuming that the situation is true. So if two angles are right angles, then they are congruent. Angle A and angle B are right angles. Well, is this the A part or the B part? Is it the hypothesis or the conclusion? Because if it's the hypothesis, then we can state the conclusion. If it's the conclusion, then we cannot state the hypothesis. So let's see. If angle A and angle B are right angles, well, two angles are right angles. That would be the if part. Okay, so we can conclude that angle A and angle B are congruent. Okay, let's see. If you lift weights, then you will be strong. Okay, so here is the A, the hypothesis. Here is the B, the then, the conclusion. Okay, well, Mr. Davis is strong. You might be tempted to say that Mr. Davis lifts weights, and it's certainly possible that Mr. Davis lifts weights. I know for a fact that Mr. Davis lifts weights, but can we logically conclude that Mr. Davis lifts weights based on this statement? And the answer is no. He could just be naturally strong. He could be like Samson. He could be taking steroids. We don't know why Mr. Davis is strong based on this statement, we cannot conclude that he lifts weights. Okay, I can only go this direction. I cannot go direction. Okay, so that's what you need to look out for, and we see that mistake all the time. Okay, moving on. Example 2. If possible, use the transitive property to write a no conditional statement. Follows from this, pair of true statements. Okay, so if a cubed equals 8, then y equals 2. All right, so again, we are assuming that this is true. If y equals 2, then 3y plus 4 equals 10. Well, this statement has this connector. Okay, these are the same. And so we can make a new conditional statement. If y cubed equals 8, then 3y plus 4 equals 10. Okay, for part B here, if the radius of a circle is 4, then the diameter is 8. Okay, we are assuming that this is true, which I believe it is. If the radius of a circle is 4, then the area is 50.3 feet squared. Now, if you're just blindly looking at this, you think, okay, well, this and this, these are not the same, and so I cannot use the transitive property. Except that this part A would actually be considered a biconditional. If I rewrite this, if the diameter is 8, then the radius is 4, well, then I would have that connecting statement. And so you got to be real careful here and be on the lookout for these biconditional statements. That's one of the ways it will try to trick you. And so we will now say if the diameter is 8 feet, then the area is 50.3 feet squared. Okay, so there's kind of a tricky one. Don't get caught with that one. All right. So here's one of my favorite type of inductive versus deductive reasoning arguments, or at least examples. So here it says use both inductive and deductive to make a conclusion about the product of two odd numbers. Well, inductively, I could do a whole bunch of examples. 3 times 5 is 15. Let's see, 1 times 7 is 7. 3 times 9 is 27. And what do I notice is the same about all of my products are odd numbers. And I could pretty conclusively say that anytime I multiply two odd numbers together, I'm going to get another odd number. Except that this proof, at least in mathematics, is not rigorous enough. And so we are going to be required to prove this deductively. Now this has quite a bit to it, so follow along and we'll show you how to do this just fine. Okay, so we're going to say given two odd numbers. So this is going to be a little bit more formal. We're going to write this out. This would be like a paragraph proof. Given two odd numbers, and then I can't just write a regular integer or a regular letter for these odd numbers because those could stand for anything. So we're going to say 2n plus 1. No matter what integer I plug in for n, that will always come out to be an odd number. Multiply it by 2, that'll make it even. Add 1 to an even number, it's going to be odd. So, but I need two odd numbers, and so I want a different one. We'll say 2n plus 1 and 2m plus 1, where m and n are in the set. So this symbol right here means in the set of integers. So the the double Z there is also the symbol for integers. Okay, so right now we have two odd integers. So given two odd numbers, okay, we will show their product is odd. And then we use kind of a word that I don't know, I was just taught to use it. We'll just say indeed. And now we will start our work. Okay? So we're going to say 2n plus 1 times 2m plus 1. And our mission here is to turn this into another odd number, 2 times something plus 1. So what I'm going to do is I'm just going to do the FOIL thing, the multiplying of two binomials. So I've got 4nm, and then I've got plus 2n plus 2m plus 1. And if I use some of my algebra skills, I can factor out a 2 from these first few terms. So I could say 2 times 2nm plus n plus m plus 1. And now let's go ahead and just be this whole ugly thing in here, 2nm plus n plus m. Well, that's got to be another integer. If all of these are integers, like I stated up here, and I multiply this by 2, it still has to be an integer. And so we're going to say that this is equal to 2, we'll call it a plus 1, where a stands for 2nm plus n plus m. Okay? And what you notice is that, well, this is in the form of another odd integer. And so we'll finish it off. We'll say, therefore, the product of two odds is an odd. And this is the form that you're going to be using for this type of proof. So you're going to set it up. That'll be the first step. Okay, tell us what you're going to do. The second step would be to actually show us. And then the third step would be to finish it off. Okay, so that takes us through some deductive reasoning. And hopefully this last example gives you a clear difference in the expectations between inductive and deductive reasoning.